Welcome back. In the second half of Chapter 11, we are going to be looking at statistics. So far, we've looked at probability, and I know a lot of people think that probability and statistics are basically the same thing, but they're actually quite different. Probability is about finding the likelihood of something happening. Statistics is about looking at data, analyzing data, and that's what we're going to be doing. Does statistics use some probability? Yes, it does, but there's a lot more to it, and it's way more entertaining. Today we're going to be looking at measures of central tendency and variation. Some of this will be review, and by saying will be review, I mean like very much review. But some of it will also be brand new to probably all of you. So we'll take a look, and we'll probably go through the review stuff a bit quicker so that we don't take up a ton of time on that. Our learning targets for today: I can find measures of central tendency and measures of variation for statistical data. Based on the title of the section, that one should be obvious. And the second one, I can examine the effects of outliers on statistical data. And so we are going to look at outliers at the very, very end. And so the first thing, we have these measures of central tendency. What are measures of central tendency? Well, we have several. 3 of them specifically you have heard of before. The first one is the mean, and we also have the median and the mode. Those are all measures of center, and that's what a measure of central tendency is. And so what are these? The mean, the typical definition people give when I ask what is a mean is they say it's the average. Kind of. Technically, all of these are averages. An average is a measure of central tendency. However, when we think of average, what we think about is the mean. We think about adding all the values and dividing by the number of values that we added. We have an equation for this. It has this big capital sigma, then xi, that would be each individual value. x1 would be the first value, x2 would be the second value, x3 would be the third value. This just means we add up all the values and divide by the number of values. We'll be using the sigma a little bit more today, and then we'll be using it actually a little bit more for the rest of the chapter even, but then next chapter we'll get into the sigma a bit more. What you need to know is it just means we're going to add up a bunch of stuff. Being that we use mean a lot, specifically in equations, the mean gets its very own variable. Now, the fun thing with statistics is instead of just using another letter, using a Greek letter, we get to give variables cool things. Like when we deal with probability and at the end of this week or the beginning of next week, we'll get a P with a little triangle above it that's called P hat. And that's just fun. The mean is an X with just a little line over it. It's a little bar. And that's actually pronounced X bar. X bar equals the sum of the values divided by the number of values. The median is just the middle number. Now, I've said this before, and people are like, okay, there's the middle number. You have to put them in order first, numerically. Then it's the middle number. It's not just the center number from a random assortment of numbers. Put them in order, then it's the middle number. And if there's an even number of numbers, and so there's 2 middles, you just take the mean of those 2, add them together, divide by 2. And then the mode is the most common number. Now, you can have 1 mode, you can have 2 modes, you can actually have no modes. You can have 3, we won't be having 3, but it is possible to have 3 modes. 2 modes is fairly common. For example, most tests are bimodal, which means they have 2 modes. There's a group of students that do well, and then not much in the middle, and then a group of students that doesn't do as well. And that's not just tests like in here, that's just tests in general. A lot of times they have 2 modes. If you have more than 2 or 3, or there's no number that really stands out as being the biggest, then it's just no modes. And so let's get some data to find these things. And we're going to get the ages of everybody in the class. And so tell me your age real quick. And good. There we go. There are the ages of everybody in the class. And we can find we can find the mean straight from here. We could find the mode from here, although that's going to be a bit more difficult. It's going to be really hard finding the median from this raw data. The very first thing we could do to this data is simply put it in order. If we put it in order, that makes things a lot easier. We have for the mean, we just have to add them up. We have 13 plus 13 plus 14 plus 14 plus 14 plus 14 plus 14, etc., etc. You can add those up. I'd recommend a calculator for a lot of what we're going to be doing. And anyway, we get 356 divided by 24 numbers, which means x bar, the mean, equals 14.833. For the median, we just have to figure out where the middle number is. We know there's 24, so if we count to 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, it'll be in between the 12th and 13th number. So there's 12 numbers here, 12 numbers here. So the middle number is the average, the mean of 15 and 15, which is in fact 15. And the mode, which one happens the most? Once we have them in order, I think that's fairly obvious that 14 happens the most, happens 9 times, whereas 15 happens 6, 16 happens 5, and 13 and 17 each happen twice. So the mode is 14. And so having the numbers in order can be helpful, but it's not necessarily the best method of displaying data. One of a better method would be a frequency distribution. In a frequency distribution, we're just going to figure out what are the possible things we could have, the individual ages, 13, 14, 15, 16, 17, and then how many times does each one happen. So we have age and frequency. So 13 happens twice, 14 happens 9 times, 15 happens 6 times, 16 happens 5 times, and 17 happens twice. One of the nice things about frequency distributions is you can do it from the raw data pretty easily. I'd use tally marks when marking them. Like we have a 14, then a 16, then another 14, then 2 15s, and a 14, 16, etc. And then you can change them into numbers. You can leave them as tallies. So with frequency distributions, finding the mean is a lot easier. We have 2 13s. If I add them together, that's just 2 times 13. 14 times 9, 15 times 6, 16 times 5, 17 times 2. Add those numbers together to get 356. Honestly, that's what I did. I didn't type each of them in individually. And so frequency distributions can be easier for that. Also much easier to find the mode. 9 is the biggest, so it's 14. The median, you can find them using frequency distributions. You just start with the edges. Hey, we have 2 and 2, so those cancel. And then 9 and 5, well, that'll take away 5 of these. We still have 4, which will take away 4 of the 6s. And so we have 2 left, so it's in between 2 of the 15s. You kind of have to imagine what's happening here when you're doing it, but you can find the median from a frequency distribution as well. The next type of distribution is called a probability distribution. It's basically the same as a frequency. We just change them into probabilities. There were 24 students, so we just divide each of these by 24. So 2 over 24, 9 over 24, 6 over 24, 5 over 24, and 2 over 24 to figure out what is the probability of each different age. And this is what we get. Now, would we do a probability distribution with this? Probably not, but we'll see one where we will in a second. But from a probability distribution, we can find what's called the expected value. The expected value is what we would expect to get on average if we picked a whole bunch of people what would their average age be? To find this, the equation, expected value equals the sum of xi times pi. That looks really confusing. I get that. All it means is we're going to take this times this, plus this times this, plus this times this, plus this times this, plus this times this. We multiply the columns in the distribution set up this way, and we just add them together. So in our case, it would look like this: 13 times 0.083 plus 14 times 3.75 plus 15 times 0.25, etc., etc. And when we multiply and add, we get that the expected value equals 14.833, which is the same as the mean. Those two things are the same. So why would we find the expected value of this? We probably wouldn't. We would have found the mean because we have this raw data. However, what if we had a carnival game or card games where we don't have a finite number of data points so much? We just have overall probabilities. In this carnival game, you can win money. You can win either $0, which would mean that you lost the carnival game, or you could win $1 or $2 or $5 or $10. And we can figure out the probability of each of these things, either theoretically, if we have something where a theoretical probability is possible, or just experimentally. We watched a lot of people play, and this is the probability. We can find the expected value. We just need to multiply each of the columns and then add them together, and we get the expected value as 0.9. And so on average, we would expect to win 90 cents. Now, something I want to point out here is, can you actually win 90 cents when you play a game? No. You can win $0, you can win $1, but you can't win 90 cents. That's okay. The expected value does not have to be one of the things, which is kind of a misnomer because it's what we would expect to get. You can't get 0.9, but it's what you expect to get over the long run. Now, this game would be called a fair game if it costs 90 cents to play, because you'd expect to get out of it what you put into it. It's a carnival game. It's not going to be a fair game. It's going to cost you $1 to play. And so, is it possible that you'll win and you'll get back your $1 or more? Yeah, but a lot of people play, and on average, they're only getting 90 cents back, which means on average, the carnival's gaining a dime. When a lot of people play, those dimes add up. That's how carnivals stay in business. Casinos as well, and lottery. The casinos don't stay in business because they lose money. On average, the house always wins. Do they lose sometimes? Yes. Do they lose big sometimes? Yes. That keeps people playing. And so it's a big science to figure out how much to charge for a game like this. Charging $1, hey, you only make 10 cents on average for every person that plays, but a lot of people are going to play. If you mess with the probability, or if you charge $2, you're going to see a lot less people playing because it's just not worth it. It's kind of like if you buy lottery tickets. Lottery tickets have, I'm pretty sure there's 6 numbers on there, and you have to match at least 3 or 4 of them to start winning any kind of money. A lot of times, people will match a number or 2 numbers or maybe 3 numbers, which you get back the money, the cost of the ticket, generally speaking. But not too many people win more than that. Personally, whenever I buy one, which doesn't happen much, I match exactly 0 numbers. That's why I don't play. But if you have a lot of people like me that can't match a single number, am I going back? No. The people that go back are the ones like, I got 2, I was so close. Next time it is going to happen. And so it's a big thing. There's actually a lot of money to be made in figuring out how to set up probabilities to get expected values and then the pay-in for it. Anyway, we don't need to worry about that. We're just finding the expected values. You multiply, and then you add them all together. In this, we get box and whisker plots. And we'll be talking about 5-number summaries because I forgot to fade that in later. So, a box and whisker plot, let's get our data back. Have our data from before in order. We need to find 5 different numbers to make a box and whisker plot. And most people have seen box and whisker plots before, and for whatever reason, they don't like them, which I have never understood. This is a really, really quick and easy graph to make. It doesn't take much thinking. It doesn't even take much time to make it. And you can see things from a box and whisker plot that you can't see from other things like histograms. And so, but they're very, very useful. So anyway, box and whisker plot, we need 5 numbers. The first number is just going to be the minimum. What's the smallest thing? And then the maximum. What's the biggest thing? We need the median, middle, and then we get these other 2 numbers that are called quartiles. We have the first quartile, which is generally abbreviated Q1, and the third quartile, which is generally abbreviated Q3, which isn't there, but we can assume. And so we can find the pieces. Now, the question that gets asked sometimes is, why don't we have a second quartile? We have first and we have third, but no second. The answer is, it's called the median. That is the second quartile. Just like, you don't have 2/4 of a dollar, you have a $half. So, our minimum, that's just the smallest number. Maximum's the biggest number. Median, we found it's the middle number, cuts it into 2 equal pieces. The quartiles are the medians of the 2 halves. So the first quartile will be the median of these 12 numbers. So we can count in 6. 1, 2, 3, 4, 5, 6. And the quartile, the median of this half, will be right between 14 and 14. What's right between 14 and 14? 14. And then in the same respect, the third quartile will be the median of this half. And so it's halfway. We have 6. It's right in between the 2 16ths. And so that's our 5-number summary. We can make a box and whisker plot from this. The very first thing you need to do in making a box and whisker plot is put down a number line. Graph paper makes it a lot easier, but a number line, because you're going to make it on your number line. One of the biggest, or 2 of the biggest mistakes I see, people will just kind of draw a random box and whisker plot, and then they'll make a number line that matches it, but the number line is all sorts of jacked up. Now, the number line needs to be evenly spaced, just like any other number line. The other thing I see people do is they actually put it on the number line itself. It does not go on the number line. It goes above the number line. It doesn't matter how far above the number line, but it does go above. And so, our box and whisker plot is going to start out with a box. It's going to go from the first quartile to the third quartile. And so we start out at the first quartile, 14. We go to the third quartile, 16. And I have it centered on a line. And I just went up and down 1 box from each of there. It doesn't, again, matter how far up or down you go. It's not about the height of this box. It's about the width of it. So we have a box that takes us from quartile 1 at 14 to quartile 3 at 16. Next, we're going to put a line in the middle of the box at the median. And then we're going to make our whiskers. Our whiskers go in the center. That's why I centered it around a line. That way I just trace the line out to the minimum and trace the line out to the maximum. And that's our box and whisker plot. Now, what does a box and whisker plot do? It graphs the 5-number summary, which splits the data into quarters. And so a quarter of our data is in this first whisker. A quarter of the data is in the middle, and then in this part of the box, and a quarter of the data is in the end whisker, which means inside this box we have 50% of our data points. And so we can see how spread out is the middle 50% of the data. In this case, it's really boring because it's all even. It's way more interesting when the median is like way over here, or one of the whiskers is super long, or something like that. But this is really boring data. A lot of the ones in your assignments won't even have enough data to really give us separate things. And so if the minimum and the first quartile are the same, you just don't even have this whisker. It's just they're both the same here. Or if the first quartile and the median are the same, the line's just at the same place, so you just have an empty box with nothing in the middle of it. If the first quartile and the third quartile are the same, then we just have some issues and some really, really lame data. Anyway, this middle box, this distance is called the interquartile range. That would be the distance from the first quartile to the third quartile. And it talks about the spread of the middle 50% of the data, how far spread out. In our class ages, half the people are within 2 years of each other. The equation for finding the interquartile range is just the third quartile minus the first quartile. In our case, 16 minus 14, which is 2. So our interquartile range is 2. Notice it's just a number. It's not 16 to 14 or 14 to 16. The interquartile range equals 2. So, speaking about range and how spread out the data is, what if we're looking at the mean instead of the median? We use variance and standard deviation for that. The equations aren't necessarily the prettiest things. Two bonuses, though, is that the equations are almost identical, and the second bonus is you're going to use your calculator to find it anyway, so the equations aren't really going to matter except for one problem on a worksheet. Other than that, you'll use your calculators, and if you take statistics in a few years, you'll use the equations like 2 or 3 times on really small data sets, and other than that, use your calculator. So what is this variance? The variance is how spread out is the data. The bigger the variance, just like the bigger the standard deviation, the more spread out the data is. The smaller the variance or standard deviation, the closer it is. If the variance or standard deviation actually equaled 0, it would mean that the data was all the same. Like our class ages would be 14, 14, 14, 14, 14, 14, 14, 14. At which point, it's really boring data. The variable we use for variance is sigma squared. And you might be thinking, wait a second, didn't he say that big random like E looking thing was a sigma? The thing that means add them all up? Yes, I did. That would be a capital sigma. This is a lowercase sigma, because Greek letters have capital and lowercase as well. And yes, they mean different things. In fact, not only do they mean different things, we're actually going to use both of them in the same equation. So it doesn't get confusing at all. And so this is sigma squared, because we are squaring it. And the equation, we're going to have a sum, so we're going to add some stuff up, and hey, look, we have lowercase sigma, uppercase sigma. But we're going to add some stuff up. What are we going to add up? We're going to take each of the data points minus the mean, so we're going to take the distance from the mean. Now, the problem is if we added all of those up, like we took the distance and added them up, we would get 0 every single time, because that's what happens. So to avoid getting 0, to avoid the positives and negatives canceling each other out, we're going to square each of those values. So we're going to go the data value minus the mean squared. So we had someone who's 13 minus 14.833 squared. 14 minus 14.833 squared. 14 minus 14.833 squared. Eventually we get to 15 minus 14.833 squared. We add all those together, and then we divide by the number of things. We actually take the average of the square distance from the mean. The mean of the square distance from the mean, even. And that's variance. Again, you'll find this once with only a few data points, and it'll take you through it step by step by step. And so, variance. Now, how about standard deviation? Standard deviation is just the square root of the variance. Why would we want to take the square root of the variance? Well, in this process, to keep them positive, we squared these distances. And so we now have a squared distance, which isn't as good. When we square root, it gets us back to the same units that we started with. And so we like seeing that more. In fact, really, the only reason why we have variance is to find the standard deviation. And so, what would we call it if we square root this? What do you think the symbol's going to be? Let's see, variance is sigma squared. If we square root, yep, that will be sigma. Equals the square root of all this stuff. Same stuff, notice. And again, the standard deviation is the one that we're going to find most often. And so, how do we find it? Well, either the exact same way, we plug it in, or we're going to use our calculators. And so, we pull out our calculators, and the very first thing that we need to do is we need to enter the data. We're going to enter the data the same place that we have always entered data. We're going to go to Stat, and then Edit. So, go to Stat, then Edit, just like we always enter data when we're doing regression lines, except now we only need one list. And oh, look, my data's already there. It's almost like I'm saving time. So quit out of that, then Stat, over to Calc, same place as we go for all of our regressions. We're going to choose the top one variable stats. We do that, list 1, frequency list we don't need, then calculate. And look, there's X bar, there's our mean that we found. The sigma x is if we added them all up. If we squared them and added them all up, oh hey, standard deviation, look at that. To find variance, we would square that number. And then, let's see, there's 24 data points. Oh hey, it gave us our 5-number summary. Well, does that mean we could probably graph a box and whisker plot? Yes. So let's go to stat plot, second, stat plot, choose the first one, turn it on, and then let's go over to box and whisker plots. This one right here. And notice when we choose it, hey, we only have one list now. Frequency 1, and then we can graph it, and we won't see anything because our box and whisker plot's way over there. So zoom stat, just like we always have, and look, there's our box and whisker plot. Notice it's up off of the axis. And so we can graph a box and whisker plot on our graphing calculator, but seriously, it's easier just to do it by hand. However, you see how we found standard deviation. You just put it in, one variable stat, mean is there, standard deviation is there, it was 1.4 something, square that to find the variance, and you have that question answered. And really, there's no reason to be finding it by hand, except for that one problem where we're going to be finding it by hand, and even then, you're going to be using your calculator to do the calculations. So, last piece, outliers. What are outliers? Outliers are data that are extreme values. They're either really, really, really big or really, really, really small, and it doesn't fit with the rest of the data. Things we can do with outliers is looking at it like if it's a mistake in gathering, like either it was a measurement issue or perhaps we were looking at the wrong population, we can get rid of it. Other than that, we tend to keep it. Now, what would looking at the wrong population look like? Let's say someone was taking data for the class, and they came in and they just asked, all right, we need all of your ages. And so we all wrote our ages down, handed it back. And they get your guys' ages, 13, 13, 14, 14, 14, blah, 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 blah. Then they get a number that's really, really, really big. What could have happened there? Oh, did I think they also meant me? Did I put my age in there? I would be considered an outlier in this classroom because, obviously, my age is like 7 or 8 times bigger than your guys' age. So we would probably throw that out because we're probably not thinking about the teachers included in the population. It's probably the population of the students because that would make a lot more sense. And so that will change the mean and the standard deviation a lot. For instance, if you included my age in the age data and you guessed my age at, say, 45, not saying that's accurate or not, and recalculated the mean, instead of coming out at 14.83, it would come out a little bit above 16. Now, is a little bit above 16 a really good descriptor of the people in the classroom? No. Almost everyone was 14 or 15. There are only a few 16s and a couple 17-year-olds. And so it pulls it a lot. And it'll also change the standard deviation quite a bit. However, the medians and quartiles are mostly unaffected. If in our data, I mean, granted, we have a lot of the same data values in our data, but if we added a big number, it wouldn't affect the mean at all, or the median. It would just move to the other 15. Like it's in between two 15s. It would actually be one of those 15s. And the quartiles would all stay the same as well, because it would just be moving up a half of a number. And so medians, quartiles are not really affected by outliers, but the mean and standard deviation do get pulled quite a bit. The mean gets pulled in that direction. Standard deviation just gets bigger. And so, how can you tell if something's an outlier? We have a couple different ways. The first is using the mean and standard deviation. It's considered an outlier if it's more than 3 standard deviations from the mean. So, if I remember correctly, the standard deviation that we were using, or that we found on the calculator, was about 1.4. So, times 3 is going to be 4.2. And the mean was 14.8. So plus 4.2, that would be 19. Anyone older than 19 would be an outlier. Minus 4.2 would give us about 10.6. Anyone below 10.6 in our class would be an outlier. And then the other way we can tell is using the interquartile range and the quartiles. If it's more than 1.5 times the interquartile range away from a quartile, it's considered an outlier. And so our interquartile range was 2. 1.5 times 2 is 3. So if we took our first quartile of 14 minus 3 gives us 11. Anyone less than 11 years old would be considered an outlier. Our third quartile, 16 plus 3, is 19. Anyone above 19 would be considered an outlier. And so we can find outliers either way, and it really depends on what we're using. Usually, we're going to be using means and standard deviations. But if we're not, for whatever reason, this is a quicker and easier way of doing it. And that's not these aren't hard and fast rules. It's just more rule of thumbs. That's kind of how we follow to determine whether or not it's an outlier. So that would be it for today. Lots and lots of information. A lot of it you already know, especially the beginning stuff. Some of the distributions, some of the expected value, generally variation, standard deviation, those are new. But mean, median, mode, box and whisker plots, things like that, you have most likely seen before several times and are probably pretty comfortable with. So, anyway, I will see you in class and have a great evening.